Welcome to Study Loop.
So in first part of this reaction problem, we have to find out which of these reactions are redox reactions. And as we know that a reaction is a redox reaction if there is a change in the oxidation number of the reactants. So in one case, or in one of the reactant species, the oxidation number will be increased, and in one other case the oxidation number will be decreased. So if we can find out such species which undergoes such kind of oxidation number change, then we'll be able to say that this reaction is a redox reaction or oxidation reduction reaction. So in the first equation, we have NH3 or ammonia reacting with oxygen to produce nitrogen monoxide and water. So first we look for um, the oxidation state of each species present here. So hydrogen, when reacting with nonmetals, has oxidation state of +1, and we have three hydrogen. That means the oxidation state of the nitrogen will be -3 here. Now, and the oxidation number of oxygen in the oxygen molecule will obviously be 0, since it's a neutral molecular state. And then in nitrogen monoxide, oxygen will have an oxidation number of -2, which is its usual oxidation state. And that means the oxidation number of nitrogen here will be +2. And also in the water, the oxidation number of hydrogen is still +1, and the oxidation number of oxygen is -2. So from here we can see that the oxidation number of nitrogen has changed from -3 to +2. That means which is increased. And as you know that the increase in oxidation number means oxidation, and there is a decrease in the oxidation number of oxygen from 0 to -2. So as you know that the reduction in oxidation number is called the reduction. So this is an oxidation reduction reaction where the oxidized species is um, or the element which is undergoing oxidation. We are simultaneously answering the part B of this. So um, the element undergoing oxidation in this case is nitrogen, and the element undergoing reduction is oxygen. So this is for the first reaction. Now we'll move to our second one. In the second reaction, you can see that again in nitrogen monoxide, oxygen has oxidation number of -2. That means nitrogen will have +2, and in oxygen will have 0, and in the nitrogen dioxide, oxygen will have again -2, and nitrogen will have since there are two oxygen, that means 2 times -2 will be -4, no, +4 for the nitrogen. So again in this case also the oxidation number of nitrogen has increased from +2 to +4. That means nitrogen is being oxidized here, and the oxidation number of oxygen has changed from 0 to -2. That means oxygen is reduced here. So this is also an oxidation reduction reaction, and the oxidized species is again nitrogen, and the reduced species is oxygen. Now in the third one, in nitrogen dioxide, we have calculated the oxidation number of nitrogen will be +4, and for oxygen it will be -2, and in water for hydrogen it is +1, and for oxygen it is -2. Now in the HNO3, hydrogen has +1, oxygen has -2, and the nitrogen will be -2 times 3 -6 +1. That means +5 for nitrogen. And in nitrogen monoxide, nitrogen will have +2, oxygen -2. So now from here we can see that the oxidation number of nitrogen. So just go for the oxygen and hydrogen first. So the number of the oxidation state of oxygen is unchanged in all the species present is this reaction mixture, and also the number of the oxidation number of hydrogen is unchanged, which is +1 in both the reactant and product side. But if we look at the oxidation number of nitrogen, it was +4 in the reactant side, but in the product side, in HNO3, we have +5 for nitrogen, and in nitrogen monoxide, we have +2 for nitrogen. So in HNO3, the oxidation number has increased from +4 to +5, but in case of nitrogen monoxide, it has decreased from +4 to +2. That means in this reaction, nitrogen is the only element which is simultaneously being oxidized and reduced. So this is also oxidation reaction where we have a change in the oxidation number, and both the oxidized and the reduced species here is nitrogen. So that answers our question to part A and part B. Now to answer the question of part C, what we have to do is first we have to find out the number of moles of the nitric acid which you need to prepare from its volume and molarity, and from that number of moles, using this balanced equation, we will find out how many moles of ammonia we need. And from there, we can find out the mass of ammonia which we'll need to prepare that number of mole of nitric acid. So first, we'll find out the number of mole of the nitric acid which we require, and that is simply its volume times the molarity. So the molarity here is 0.150 molar or mole per liter, and the volume here is um, so from the volume we can see that it is an 1000 liter. So multiply this by the volume 1000 liter, and this will give us a value of 150 mole. So this is the number of mole of nitric acid we need to prepare. Now from the balanced equation we can see that 2 mole of nitric acid is prepared from 2 mole of nitrogen um, dioxide. Oh no, it's 3 mole of nitrogen dioxide. So uh, let's just, so it will be 3 mole of nitrogen dioxide here. So that means 2 mole, it's HNO3 is prepared from 3 mole nitrogen dioxide. That means 150 mole HNO3 will be prepared from 3 by 2 times 150 mole, which will give us a value of 225 mole of nitrogen dioxide. So 225 mole of nitrogen dioxide is required to form 150 mole of HNO3, but we are here to find out the number of moles for the ammonia. So we'll have to go backward to find out the number of mole of ammonia we need. So from the second equation, we can see that 2 mole of nitrogen dioxide um, is prepared from 2 mole of nitrogen monoxide. That means the number of mole of nitrogen dioxide to prepare is same for the nitrogen for the number of mole of nitrogen monoxide. So that means 225 mole of nitrogen dioxide will be formed from the 225 mole of nitrogen monoxide. Now we go to the first reaction. So here we can see that 4 mole of nitrogen monoxide is prepared from 4 mole of ammonia. That means 225 mole of nitrogen monoxide will be formed from 225 mole of ammonia. That means just from here to here, we can see that to produce 150 mole of nitric acid, we need 225 mole of ammonia. So the number of mole of ammonia which is needed is 225 mole. Now from here we can find out the mass of ammonia which we need. Just as we know that the number of moles is mass over molar mass, that means mass equal to number of moles times the molar mass. So the molar mass of ammonia is 17.02 gram per mole, and it will give us a value of approximately 380 3825 gram ammonia. So this is the mass of ammonia which is required, or which we must start with to make this much aqueous solution of nitric acid.